Sorry about that. Okay, so I'm going to wrap up Chapter 1 by talking about elements, the difference between elements, compounds, molecules, and talking about how to draw and write chemical formulas. So let's talk about what elements are. Unfortunately, we're not really going to get into the real nitty-gritty of what an element is and how it's different from another element until about Chapter 3. I'm just going to talk about elements sort of as these. We're going to start off just talking about kind of as like mystical things for a little bit, and I'm going to talk about them kind of in the abstract. We'll really get into dissecting them a little bit later. Right now, know that there's about 117 known elements. I might be behind by a little bit, but it's about 117. Your periodic table in your book probably doesn't even have that many. Nope, it's up to date. I just looked. We just haven't found 117 yet, or maybe I'm forgetting that we did. Anyway, 88 of them are naturally occurring. I know that hasn't changed even with any recent news, because most of the new elements being discovered are being created in labs. And we'll talk more about that. I'll be able to go into more detail about why that is and what the significance of that is when we get into Chapter 3. The universe is dominated by a small number of elements, hydrogen, helium particularly. That's really what the universe is mostly made up of. There are these weird little pockets in the universe of other bigger, heavier elements. So like the Earth is a weird collection that doesn't really represent the distribution in the universe, which I said is mostly hydrogen and helium. The Earth's crust is mostly oxygen and silicon, so we get this kind of weird collection of elements here. However, each element, regardless of where they came from or what the distribution is, has a set of properties. So I could describe oxygen as being the thing that makes a molecule of two, and we can breathe safely and ignites. And I could describe it in a lot of ways. But we summarize all those properties by a name, oxygen. And nitrogen has its name, so we summarize everything by a name. We further abbreviate it by a symbol. So instead of trying to describe oxygen, we call it oxygen, and it has a symbol O. Now, if we look on the periodic table, which I'm going to go grab one. So if we look at a periodic table, this is kind of a fancy one, but you have just the elements list up here in the boxes. And we'll talk about, through the course of this class, we're going to talk about the significance of all these things, these numbers here, these numbers here. Right now, all I want you to pay attention to are the symbols, and that these symbols represent certain names. So here's carbon, oxygen, nitrogen. Each element gets its own box on the periodic table. And so this is all we do have 117, sorry. So there's 118 elements now known. Like I said, we refer to these elements by their names, and these have these further abbreviated symbols. So the chemical symbol is a 1 or 2 letter symbol that stands for the name of an element. Only the first letter is ever capitalized, so that's how we can tell the distinction between some of these things. So if we look at the periodic table, see all the 2-letter elements, the second one is lowercase. So that's how we can tell the difference between, for example, chlorine and iodine, capital C, lowercase l, capital I, and carbon and lithium. Not that these compounds ever actually form, but carbon and then one capital and then capital lowercase, so carbon, lithium. Okay, so if we have one element, oxygen, if I had a big tank of oxygen, right, I have a bunch of oxygen here, right? There's actually lots of oxygen molecules here. But I can take this, and oxygen has a certain set of properties. If I take the tank and I divide it in two, and I take this half now, it still has the same properties as the larger amount, but just there's less of it. If I divide it again and I take this half, and I'm not really cutting them in half very well, but here, and I keep doing that and I get smaller and smaller halves, I will get down to a point where I have the smallest thing that can be considered oxygen. If I cut it any more, I don't have oxygen anymore. I've changed what it is, right? At a certain point, we reach the smallest unit that still has the properties of our element. This is considered an atom of oxygen, so an oxygen atom. The smallest unit of any element is an atom. So these are the building blocks. And we'll actually talk about atoms in a lot of detail in Chapter 3. But an atom is they're too small to see with the naked eye, and they're the smallest they're the little building blocks that the elements are composed of. And we use these as building blocks. So atoms of different elements, or the same element, can combine together. So remember, if I combine atoms, physically, it's still just a mixture. It's not until they chemically bond together that we get more complicated pure substances. Now, if I bond together two atoms of the same element, like oxygen, right, that's still an element. Right? Remember, it's still an element. But now there's two of them bonded together. And I have a name for this in a moment. If I bond together a carbon and an oxygen, that's a compound, right? It's two different elements together. Now, the term for this, so this one is an element, this one is a compound, but they are both molecules. Molecules are two or more atoms that are bonded together chemically that function as a single unit. Now, molecules can be elements or compounds. If I have a molecule that's an element, I'm just referring to something that's got all the same element in it. A molecule that is a compound has two or more different elements in it. So C60 is a molecule that is an element, but it's an element. And then H2SO4 is a molecule that's a compound. So, we have some other terms that we use to describe molecules. So, diatomic, we're also going to have triatomic and tetratomic. So in that context, diatomic, what does di mean? Di means two, and atomic is talking about atoms. So diatomic is a molecule. A diatomic molecule is a molecule that contains two atoms. Again, I'm not making any claim as to whether or not these two atoms are of the same element or different elements. That's a different criteria. So O2 is a diatomic molecule. CO is a diatomic molecule. They're both diatomic molecules. One's an element, one's a compound. Triatomic, three. So CO2 is a triatomic, O3 is triatomic, H2O is triatomic. Remember, I'm not talking about how many different elements there are. So if you see, H2O is triatomic because it's got two hydrogens and one oxygen. So a polyatomic molecule just has more than three. There are terms, tetratomic, penta, hexa, hepta, octa. I'm not going to really make you know these, at least for now. We're going to use them later in a different context. Molecules can be heteroatomic or homoatomic. So as we talked about before, hetero means different, different atom. In other words, heteroatomic molecules have two or more, could be more, different types of atoms, two or more different elements. So in other words, a substance that exists as heteroatomic molecules is a compound. Later, we're going to talk about how not all compounds actually exist as molecules. This is a weird thing. Just put it aside for now. Just know that it's coming up later. Just know that it doesn't work in reverse. Not all compounds necessarily are heteroatomic molecules. Homoatomic molecule. Homo means same, so we mean only one type of atom. So a heteroatomic molecule would be H2O. Now, I can call this a triatomic heteroatomic molecule. O3 is a triatomic homoatomic molecule, right? It's an element. So, I said this before, compounds are composed of two or more different elements chemically bonded together. It doesn't matter how many are there or how many are in each molecule. A substance with 6 phosphorus atoms is still an element. It's only got phosphorus in it. Formulas, I've been using the formulas, and maybe you caught on to what I'm drawing and maybe you haven't, but I'm going to explain them a little more formally now. Chemical formula is the concise notation to describe what's going on in a formula unit or a molecule. I'll talk about why some things aren't molecules later. But basically, For right now, we're just going to pretend everything's a molecule. I'll just call everything molecules. So, chemical formulas contain the symbols of every type of element present in the unit, carbon and oxygen. So here we've got 1 carbon, 1 oxygen together. We use some scripts if there's more than one. So as a rule in chemistry, as a general rule, if there's only one of something, we don't put a 1 after it, or later when we put them before, we don't put the 1 there. We just leave it alone. So just an element without a number after it there's just one of them in that unit. If I have CO2, that means 1 carbon and 2 oxygens. Fairly simple. Sometimes you're going to see parentheses, like this SO4 is in parentheses. We'll be able to explore a little bit later why it's in parentheses, but for right now, just accept that what we have here is we have 2 aluminum atoms, and what we have is we have 3 units of SO4. So that means that overall we have 3 sulfur atoms and 12 oxygen atoms, right? Because these SO4 unit is repeated 3 times. I think that's really all I have to say. This pretty well wraps up Chapter 1. So we'll move on to Chapter 2 shortly. So make sure that if you have any, feel free to review any of these videos, this one and the other ones I have for Chapter 1. Make sure that you're getting your questions recorded. If there's something you're not understanding, make sure you bring it up with me. I'm happy to talk about it in class, and I'm even happy to make a video clarifying something if you need help, because it may help others. So let me know. I'm here to help.